So good afternoon, everybody. Those in Abu Dhabi, thank you so much for being here in another session of our Quantum Research Center seminars. It's evening for those in Abu Dhabi, so I especially thank you for staying so late in Ramadan time, which is not so easy in the office. For those in the office, I thank you so much. And of course, I thank our speaker, Stephen Walborn, Professor Stephen Walborn, who's currently in Concepcion in Chile. Concepcion is a nice city south of Santiago in Chile. And it's morning time for us. I think that for Steve is, what is it, 9 in the morning? For me here, I'm in Argentina at the moment, it's 10. So it's morning time for us. And I'm going to make a little introduction of Steve. It's again difficult for me because I'm a big friend of Steve. So many personal things get mixed. I always say that Steve is the strongest experiment. Yeah. So I always say that Steve is the strongest quantum information experimentalist I know in Latin America. He's a very strong experimentalist, one of those cases of experimentalists that understand theory very, very well. I had the honor of had him. I was a PhD student when he was a postdoc in Rio, and we even wrote theoretical papers together. So Steve wrote several theoretical papers too. And Steve did a master's in the University of Minas Gerais, in the Federal University of Minas Gerais, and PhD also there, I think. Then he went for a postdoc in the Federal University of Rio de Janeiro. He eventually became a professor there and received important prizes and awards in Brazil at the national level. He's been doing quantum information experiments on fundamental topics, steering, non-locality, foundations of measurements, and measurements of entanglement. He's published several high-impact papers on detecting entanglement in different systems. And for a few years now, I think since 18 or 19, you've been in Chile since 2019 or 2020 was that you moved. So since
November
then, Steve
2019. Yeah.
November 2019, Steve is a professor in the University of Concepción in Chile. There's a very, very strong group there. The one that started that was Gustavo Lima, and now the team got even stronger because they got Steve. And since then, he's been doing there different things on high-dimensional quantum information with photonics. And yeah, it's really a pleasure to have you here, Steve. I thank you so much for your time and for your availability. It's really a pleasure to have you here. And please know that you're welcome to visit us personally whenever you want and things get more normal in Abu Dhabi. So you have an open invitation. Thank you so much. Please go ahead, Steve.
Okay. Well, thank you very much for the invitation to visit. I will definitely take you up on that as soon as I can. So you can see the cursor, yeah? Mm-hmm. Okay. I'll try not to use it too much, only when it's extremely necessary. So yeah, thanks for the introduction, Leandro. Also, thank you for the invitation to give this talk. So the title of my talk today is Multicore Optical Fibers for Quantum Information Processing. It's maybe a little bit more technical than what a kind of talk I would normally give. And I'll tell you why that is in a moment. So I'm at the University of Concepción now since for a little bit over 2 years. I'm also part of the Millennium Institute for Research in Optics, which is an institute, it's kind of a virtual institute here in Chile with about 10 researchers. And it's nice because it gives us access to some pretty good funding. And we're funded mostly through the Chilean government. So at UDEC, let me just mention in the Concepcion region, let me mention who is working in quantum optics, quantum information. So at UDEC, we have two theoreticians, principally right now, Professor Aldo Delgado. Carlos Saavedra is actually right now the rector of our university, so he doesn't have very much time to think about science, at least research. So he's quite busy leading the university. So on the experimental side, actually the nice thing here is we have quite a few researchers. And so as Leandro mentioned, the experimental activities were started here by Professor Gustavo Lima. And then there's a couple more of us who have joined since then. Some have been students of the group and so on. And so I mentioned here in bold, I have Gustavo Lima and also Guilherme Xavier, who has unfortunately, he's moved to Sweden a few years ago. And I have them in bold here because they were responsible for bringing this multi-core optical fiber technology to our lab, and they really started this line of research that I'm going to present today. There's a few more of us, and there's also two experimentalists that we collaborate with at two other universities here in Concepcion. And kind of a really interesting thing here from an experimental side is that we have pretty strong collaborations with some professors in electrical engineering, which gives us access to all the knowledge and techniques and know-how that engineers typically have, in particular in programming these FPGA devices, which we use to control the experiments and other things. And so they work basically also in telecom stuff. So yeah, so here's a brief outline of what I want to talk about. As I mentioned, it's going to be a little bit more, say, technical talk. And the reason I'm going to have this approach is for a purely selfish reason, is that I want to convince you that we have something interesting here, an interesting platform. And I want to show you the kinds of things we can do in hope that we can have some collaboration and things like this. So I'm going to show some of our results. I'm going to show kind of what we have, give, why we think it's so what we have are these multi-core fibers and fiber devices. What we want to do is photonic quantum information. So I'll talk about that in kind of an introduction. And I'll present some of our recent results to give you examples of what we can do. And I think some of these results are quite quite interesting. In particular, one thing I really like this idea for generalized quantum measurements. So here we go. So of course, there's quite a bit of interest in photonic quantum information for a number of reasons. The kind of main reason is that, of course, anything we do in terms of implementing quantum technologies, photons will most definitely play a part, because it's the way we can transmit quantum information from one place to another over, larger distances. So there are, the flying qubits that we have access to. If not, I mean, photons or some light, quantum light in general. And so one of the kind of main ideas here is that, well, if we're really going to have, say, quantum networks and do large-scale quantum communication, we're going to have to be able to take advantage of the whole telecommunications infrastructure and the technology that's available from the telecommunications. So yes, that means like having quantum systems that are functioning in parallel with the quantum communication schemes and so on through the same kind of fibers and devices. So when you work with photons, of course, one kind of appealing thing from a more fundamental side is that there's many different degrees of freedom that you can choose from, and so depending on what your system looks like, or what sort of thing you want to do, you can choose different degrees of freedom, and we'll talk about that more in a moment. And so, of course, with these multiple degrees of freedom, you can do higher dimensional encoding of quantum information. So, and I'll talk about that again. And so, I mean, the main reason that we're interested in higher dimensional encoding is that you can, of course, encode more information, which is, kind of you would think is a good thing. But there's also certain scenarios in quantum information where you need more than a single qubit. The main example would be in quantum contextuality, which you can observe with a three-dimensional system or larger. So this is kind of motivations, some of the motivations to work with photons. So as I mentioned, there's a number of different degrees of freedom you can work with. There's kind of the most common would be polarization. So this is just like polarization of light, but you can create single photon states which have all the same properties, polarization properties of a light beam. So you can define a computational basis, typically with, say, horizontal and vertical linear polarizations. And the kind of real nice thing here is that there's all sorts of technology for the manipulation of the polarization of light. So wave plates and different birefringent materials, and polarizing beam splitters, which do really high quality measurements, and so on. So you have this whole toolbox of things you can, toolbox of equipment you can use to prepare and measure these polarization states. The kind of one of the downsides of polarization perhaps is that it's a little bit tricky to use when you want to send light through optical fibers, because the fibers themselves can be birefringent. So the polarization, you can get essentially the equivalent of dephasing as the light and depolarization as the light propagates through the optical fiber. So what we're going to talk about in the talk today is momentum encoding. So if you want to encode a qubit, you can imagine two different propagation directions, and you can put the photon in either the upper level or the lower level and call that 0 and 1. And this is kind of the canonical scheme for encoding, because you can use very simple devices to perform logic operations. So to put a controlled phase, or to put rather a relative phase on these modes, you just put some sort of device like a piece of glass or something in one of the modes. And you can do rotations in this computational basis through beam splitters. So if you have a beam splitter that you can control the transmission and reflection coefficients, you can perform this type of operation down here. And so there's several theory papers showing how you can construct general unitaries with these two basic devices. So just to kind of, for sake of completeness, I also want to mention this idea of using transverse spatial modes. So these are eigenmodes of propagation. And originally were studied in terms of laser resonators. So they're eigenmodes of these laser resonators. They're also, if you make some minor adjustments, are eigenmodes of free propagation. So they propagate, they just diverge, they don't change their structure. So you have these different, in this on the left-hand side of the leg is the Laguerre-Gaussian basis. And so you have these different mode numbers, which name them. And when you have this mode number L different from 0, these modes have orbital angular momentum. So this has been studied quite a bit for quantum communication, in particular in free space. And there's an interesting thing here, is that if you want to think about propagation through fibers, in particular multi-mode fibers or fibers with different structure, you can find similar modes that are eigenmodes of the fibers. So you have kind of an analogous basis when you work in some different types of fibers. Finally, you can of course go to the frequency and time degrees of freedom. So here's one encoding, which is called time bin. So you can just imagine two different time slots for the photon, kind of really analogous to what you do with linear momentum. So the photon can be in the first time slot or the second time slot. That's your computational basis, 0 and 1. And you can imagine devices that will prepare or measure different qubit states in this encoding. So all these are completely viable and interesting ways to encode information. So when you start to think about, okay, well, how much information can I code and what system should I use? Of course, for all these degrees of freedom I mentioned, except for polarization, you can encode kind of as much information as you want, or as you can. So you're not limited to only two modes as you are in polarization. In linear momentum, for example, you can imagine many different modes, and you can imagine combinations of these different degrees of freedom. So you can you can imagine encoding quite a bit of information in a single photon. Another interesting thing about this type of idea is that you can perform deterministic gates, deterministic unitaries in higher dimension. And so using a number of these different devices I mentioned, you can construct the operations you would want to do. So the idea is okay, can we use this, and kind of how far can we go with this? And so the first idea you might have is, okay, well, maybe I can just, if I can encode as much information as I want, maybe I can just build a quantum computer with a single photon. And of course, this has been known for 20 years or so that this type of approach is not scalable. And so because you have this exponential growth in the number of different modes you need to encode, say the equivalent of n qubits. So you need 2 to the n modes to encode the equivalent of n qubits. And so the one interesting way to look at the consequences of this is if you just imagine, all these modes lined up like you would have in some sort of interferometer. So it doesn't matter really what degree of freedom you encode in. Eventually, you have to you have something that looks like this, especially when you do measurements, right? So if you think, okay, well, the minimum spacing between these modes is going to be about the order of the wavelength of light, And so if you want to encode n qubits, you need an interferometer that would be this, have this dimension parameter d, which would be something like 2 to the n times lambda. So if you just pick a kind of a modest number of qubits, say 40 qubits, you would see that this interferometer would have to be 1,000 kilometers wide. 2 to the n is about 1 trillion. So a trillion wavelengths wide. So this is just kind of, you know, an example of why this type of encoding can only take you so far. From a more practical point of view, and kind of the kind of thing you think about when you're running a lab is what I call the detector issue. So currently, I mean, the detectors are one of the most expensive components in these photonic setups. And so, of course, if I want to encode, say, 40 qubits encoded into 40 photons, suppose I can produce 40 photons on demand or whatever. So I need, 2 detectors for each qubit to detect, say the 0 and the 1 state. And then I would need 40 photons, so that would give me 80 detectors. On the other hand, if I'm thinking about a single photon in 2 to the n or 2 to the 40 modes, I need to buy over 1 trillion detectors and put them somewhere. So this is, even if you go to more modest numbers than the equivalent of 40 qubits, you go to say 8 qubits or 8 photons, which is done today in the world, you still have quite an expensive price tag in this single photon encoding. So on the other hand, there, in terms of, so I don't want to get, my arguments in the past 2 slides have been very negative. On the positive side, you have, of course, the detectors have a limited efficiency. They're not perfectly efficient in detection of a photon. You also have losses in your system. You can't avoid this. So you have some kind of overall efficiency eta, which is, can be much less than 1. So if you want to detect, if you want to, use this multiple photon encoding with, n qubits encoded into n photons, you have an efficiency, overall efficiency that goes to the n power of eta, which can be quite small. With a single photon encoding, on the other hand, you have the efficiency just goes as eta, since you're only detecting a single photon. So there's, pros and cons, there's arguments, in favor, arguments against, and kind of the moral of the story here, this is of course, in my opinion, is that this high dimensional encoding is of course interesting. As I mentioned, it's necessary for some types of quantum protocols, but there's kind of a sweet spot here in terms of the dimension. And I would say it's somewhere between 2 and 8 or so. So kind of depending on how much money and space you have in your lab, this is kind of where you want to be working. So I just say this because I see, papers talking about high dimension, but this is something you can only really realistically take so far. So let me switch gears now and talk a little bit about this, about optical fiber technology. So right now in telecommunications, and again, this is not my field, but this is kind of a brief summary of the current scenario. So this plot here shows basically the amount of data you can encode into an optical fiber based on per year, right? So from 1980 to close to the present day. And so you can see here that this purple line kind of shows you what the trend has been. So the amount of data increases by a factor 10 every 4 years or so. So this is kind of like a Moore's law of fiber optics. And so the different encoding techniques, like for example, wavelength division multiplexing here in the middle, they are able to multiplex more and more information into an optical fiber. But you can see up top here, there's this dashed brown line. And this is what's known as the capacity limit. And so basically, it's once you reach this line here, you've crammed so much intensity into the light intensity into the optical fiber that now you have nonlinear effects and so on, which create crosstalk between the different frequency modes and so on. And you start, if you try to put more information into the fiber, you actually have a decrease in information transmission. So this is for a fiber. All of this has been done currently with fibers with a single spatial mode. So the way that the proposal to go beyond this is through space division multiplexing. And so the idea here now is the same way you use different wavelength channels to encode information. Now you can use different spatial modes as different channels within a fiber. So a number of different fibers have been proposed, different types of fiber have been proposed to do this. I'll talk about that in a second. And just, there's been some, research showing how you can go beyond this limit with this approach. And this is, as far as I know, this is the only kind of way to go, because they'd exhausted all the other types of tricks you could do with optical fibers to put information. So this is something that it seems like is going to happen, this transition from single mode fibers to some sort of spatial encoding as well. So this is a plot from, or a figure from a paper that Gustavo and Guilherme Xavier wrote one or two years ago. So this kind of are some examples of the fibers that are currently being investigated. So what we'll talk about today is this multi-core fibers. So this is a fibers that have a bunch of different cores within the same cladding material. So the light propagates to these little black regions. So these are single mode cores within a cladding. You can also have fibers that have cores that are slightly larger that allow for propagation of few of these spatial modes. So you would have several transverse spatial modes propagating in the same core. You can also have ring core fibers, and these are the type of structures that where you can have these orbital angular momentum eigenstates propagating in the fiber, and all different combinations of these. So you can have few mode, multi-core fibers, and so on. So what I'm going to talk about today in this talk are these multi-core fibers. In our lab, we also have some ring core fibers, which we're starting to work with. But today we'll talk about these multi-core fibers. And so these are independent spatial channels, and the way there's really is like almost zero crosstalk between these different cores, and that's because, well, they're quite far apart. And also you can put this trenching structure in the refractive index. So basically, this prohibits light from escaping one core and coupling to the other core. So these are essentially independent spatial channels in the same cladding. So the approach for this in terms of quantum encoding is again, we're going to have say d different modes. So this will form our computational basis. So a photon in one of these d different modes, a general state is going to be kind of a superposition of these states. And this is, so what we'll talk about for most of the talk is this type of structure here. So we have 4 core fiber that we label the different cores according to these different kets we define. And here's an image of one of our fibers just taken with a fiber microscope. So the cores are about 8 microns wide. It's single mode fiber for telecom wavelengths. And the distance between the cores is about 50 microns. So the key point here, or kind of aside from the technological side where, okay, this is going to be, the future of telecom is in this, with these types of structured fibers. The appealing thing here for quantum photonics is that because these cores are embedded in the same cladding, you would expect that there's going to be a lot better phase stability between the different cores. So of course, if you have this superposition state here on the right, and you have some random relative phase, on one of the modes in relation to the other ones, you destroy this superposition and you have some sort of mixed state. So this phase stability is a really appealing thing here on the quantum side. So here's data from, or a plot from a paper published by a group in Denmark. And what they did is they built a 2-kilometer long interferometer. And so when they will build this interferometer with single mode fiber, you have these purple data here. And when they build the interferometer with 2 cores of the same multi-core fiber, which is this red and orange data here. And you can see that the purple data fluctuates, several, you go from maximum to minimum of interference, multiple times in a single second, which is shown in the inset here. Whereas the multi-core fiber, you have stability over the range of a few seconds. So this is kind of just a demonstration of that. Indeed, it is the case that there's a lot more phase stability with the multi-core fiber.
So can I ask something?
Yes,
so why is the I think I don't understand the horizontal, the vertical axis. Why is the contrast between the two different? If I look at the, maybe they're differently scaled, or
it's cut here. So for the purple data, the 0 starts here and goes up to some some maximum, and then for the multi-core data, there's a 0 here. So yeah, I agree that I looked at that a few times when I first saw this plot. Yeah, so it's the contrast is essentially the same. It's 2 different plots shown one on top of the other. And so this is on the horizontal axis is seconds here. So over 30 seconds of data, you can see the purple data is going crazy, whereas you have, a few seconds of stability for the orange and red data. And this is, I mean, because the cores are in the same cladding, temperature differences and so on are much less between the two different cores.
And the two separate fibers, they were like, how were they? They were running exactly next to each other, I guess. So they try to bring them as close together as possible. Or?
Yeah, I mean, they're made mechanically, in all the same mechanical devices. So I mean, mechanical fluctuations so on should be the same. It's just that the difference in temperature changes and so on within the fiber.
Super, thanks.
Sure. So to take it, so the idea is we're going to use these multicore fibers as your quantum channels. And so to really take advantage of this, you need a few more devices. And so one of the devices is this multiplexer or demultiplexer device, which in telecom they call the MOOCs or the DMOOCs. And so this basically allows this, you can attach single mode fibers to these multicore fibers in such a way that you can send light through a single mode fiber into one of the cores of the multicore fiber, or do the opposite. So this is how you can couple light in from your laser or whatever, and how you can couple light out again, to send it to a detector or to phase modulators and so on. So this is one device which you can buy commercially. Another device, which actually, it was, as far as I know, is Gustavo and Guilherme who really pushed one of the fiber manufacturers to build this device, which is the 4x4, which is the multicore fiber beam splitter. So we have these for 4-mode fibers and also for 7-mode fibers, but really you can make them for whatever fiber you want. So the idea is, I mean, you basically heat the fiber and you stretch it so you have this tapering here. So the cores become closer together in this region so that light can actually couple from one core to the other. So I should mention that the type of fiber you use to make these structures does not have those trenches, which I mentioned. So basically, once you bring the cores close enough together, light can couple from one core to the other. And the nice symmetry in the 4-core fiber, for example, gives you a matrix that describes this transformation, which is given by this. It's essentially, it's really close to a Hadamard matrix. So this is the data from quantum process tomography, which is done on one of these devices. Of course, every device is a little bit different, but they're really close to this 4x4 Hadamard matrix. And of course, okay, so the reason from the quantum approach, the reason you need this is because you want to be able to produce superposition states. And so produce and also detect superposition states. On the telecom side, the interesting thing about these things, you can use them to build optical switches in the multicore fiber, which is something that they're doing in our lab also. Okay, so the first thing that was done a few years ago, just before COVID arrived, was to build a four-path interferometer. So basically, this is your typical fiber interferometer that uses these multicore fiber beam splitters, and so you have these demultiplexers to go in and out of the beam splitter. And then unfortunately, the current scenario is that in order to imprint different phases on the different cores within the fiber, we have to actually couple out of the multicore fiber and use single mode fiber phase modulators. So this is actually a current challenge right now, is to build some sort of phase modulator that can modulate the phase of the individual cores without taking a light out of the multicore fiber. So this is something which we hope will become available sometime soon. But for now, this is the type of thing you have to do. So this is kind of so you couple light out of the fiber. Alice can modulate the phase. The light could then go back into a multicore fiber, but here in the setup, the light goes straight to Bob, and who can modify the phase and then send it through a beam splitter again and detect it. So this is kind of a general prepare and measure device where you can prepare generalized superposition states of a single photon in one of 4 modes, and then you can detect them in a general superposition basis. So this device, which we first built, uses weak coherence states as an input, so it's kind of an approximate single photon coming in. And so because of the really high quality of these beam splitters, we're able, what really sets this device apart from others, I think, is that we have really high quality interference, so greater than 99% visibility. And we have this active phase stabilization. And not only that, but I mean, this is all telecom technology. So, I mean, in principle, you can modulate this kind of as fast as you can, I mean, as fast as you want. The phase modulation is extremely rapid. The bottleneck here is in the detectors. I mean, the detectors can only work at about, say, 10 megahertz or so. But I mean, so these phase modulators are gigahertz phase modulators, all from telecom. So here's some data showing what happens. So if you turn the device on, the phase modulation starts to work, and then after about, say, 50 seconds or so, it finds the spot, and so it stabilizes the phase. Oh, sorry. It can stabilize the phase. So in typical experiments, what you do is you're kind of switching back and forth between, you know, say a fraction, stabilizing the phase for a fraction of a second, and when you have reached the stable situation, then you go to a measurement stage in which you apply different phases and perform a measurement. So this is on the bottom graph here is just the interference curves when you change one of these phases, and you can see there's these high quality interference fringes that you see. So this is a really nice device in that it's all automated and a really high quality interference. So I want to mention some of the things which we've done with this type of setup. So the
ask
first
something
thing
again.
Yes, please.
So you said what sets your device apart from others is that you have a very high contrast. Your 99%.
Yeah, the contrast and also the velocity of modulation, which we're able to achieve.
Yeah. And can you say what you did differently, or what's the key idea there to get the high contrast? I think I know normal 2x2 splitters, and I think they have a decent contrast. Well, what do you have to do to get a high contrast?
It's just in the fact that the multi-core fiber beam splitter. So it's as I showed, it's just really these devices are really high quality. I mean, the split ratios that you achieve in coupling light from one core to the other three cores is, I mean, nearly perfect. And this is just based on this is fabricated with, sophisticated fiber fabrication devices and these taperings and so on. And so you're able to achieve this. If you would want to, say, build this device, and the other I guess key point here is that it's a multi-port device. So it's coupling light from one mode to the three others, all in the same interference region. Whereas if you would want to build this with, you could build the same sort of thing with a couple of 2x2 beam splitters, but that would require at least, I guess, 3 beam splitters. So if you would have a kind of a slight error in each of them, and that error starts compounding as you chain them together. So yeah, it's really like a technical aspect of these devices that are so good. And then, I mean, of course, just the whole setup. I mean, the fact that we can actively stabilize the phase, and it's all computer controlled, and and of course the phase modulators are really high quality because it's off the shelf telecom components, which, I mean, these sort of things have been developed by industry for a few decades, and so they're really high quality devices.
The active phase stabilization, how does this exactly work? Do you do this via temperature? No, you do it faster somehow.
No, so we've controlled the phase modulators here in the setup. So you can basically so we use the actual, so we send say pulses through the interferometer in the stabilization phase, and we basically run an algorithm that tries to send, we send light through all four, split the single photon pulse through all four of the fibers, and then we try to adjust the phase so that it exits in a single detector. So,
so you have, okay. This means you actively stabilize the phase of each channel individually.
Exactly. So that's why here you can see it takes about, say when it first turns on, it takes about 50 seconds until it finds the right, set of phases, and then stabilize it. And once it's found the stabilization, then you can kind of switch back. You can say, okay, I'm stabilized. I'll do a measurement. Then you go back and you check the phase again. You say, okay, we're still good. Do another measurement. And then, we lost the phase. You wait until you find it again. And so all the measurements are done in this routine of stabilization and measurement.
And why do you lock to a maximum or to a minimum and not to the steep slope? Is there like an advantage there? What is the thinking there? It looks like.
To be honest, I'm not exactly sure. It's the way this particular algorithm works was most advantageous and easiest, I guess, to lock to the maximum.
Okay.
Yeah. I mean because I mean this type of algorithm was adapted from what you would do is say two-mode interferometer. So I guess the reason is because we have four signals, right? So it's easiest if you try to maximize the counts in a single signal, right? Or you try to minimize these three or maximize this one.
Mm-hmm.
Yeah. Okay. Yeah, I mean, actually, that's the reason, because if you look at what happens in the slope regions here below, you have kind of different counts for all four of the detectors.
Last question for this. And then what is now the advantage of having them all in the same fiber? Because it looks like you do a lock to each of the channels. You could also do if they were separate.
Yeah, so as I mentioned, in this, the reason, so in this particular experiment, I mean, we have to take the fibers out of the light out of the multicore fiber in order to modulate the phase. So if we wanted to put, say, a channel between Alice and Bob, we could send the light back into the multicore fiber, send it over some distance, and then Bob would have to take the light out of the multicore fiber to do his measurement and modulate the phase. So this is just because we don't have phase modulators that work in this multicore fiber structure yet. So this interferometer doesn't necessarily take advantage of the multicore fiber for transmission. It only takes advantage of the beam splitter, say.
Okay.
So let me mention some experiments that we've done. So you've probably seen this experiment. It's basically with this multicore fiber, we're able to experiment indefinite causal order of more than two quantum gates, and actually we did this experiment in collaboration with Leandro. And so the point here is like the multicore fiber is extremely convenient for doing these types of quantum switch experiments. So kind of the main idea here is that, I mean, typically in quantum information, you apply gates, sequentially in some causally ordered sequence. So you apply gate A, then B, and have some output state, or you apply B, then A, and have some output state. Of course, quantum mechanics allows you to do this routing coherently. So, I mean, assuming you can route your quantum system coherently through A, then B, or B, then A, that you're allowed to do this, right? And so I like using this word route because I think this shows how photons are particularly interesting for this type of scenario. I mean, typically A and B are some sort of macroscopic device that performs a quantum gate, and so you have to be able to physically take the easiest way or most kind of direct way of doing this type of experiment is to physically take your qubit and send it through A, then B, or your quantum system through A, then B. So this is something that's this routing is something that's been called the quantum switch. So in our experiment, so quantum switches with two different operations have been done by several groups. And so what we were able to do a few years ago was do a quantum switch with 4 operations. So some sort of routing structure was chosen so that the photon goes through A, B, C, and D in some order. There are 4 different possible sequences, and which was shown in this paper that I showed was that this type of structure allows you to solve, say, like a kind of toy computational problem faster than even a fixed order quantum computer. And so in our experiment, kind of a nice aspect here is that we can use, of course, the spatial mode as the control system. So the 4 different spatial modes are these different colored curves here. And then the polarization of the photon is now the target system. So that means that these unitaries, we can take advantage of polarization operations to rotate the polarization. So A, B, C, and D are actually liquid crystal wave plates. So we can turn them off and on electronically. So this is a diagram of what the experiment looks like. So it's basically, again, this 4-mode interferometer with the beam splitters, and then we have this quantum switch device constructed in the middle. And from all these different arrows, which I'm not going to go through the sequence, but basically using this multi-core fiber, we route the photons through the different wave plates in different orders. And just the multi-core fibers make this quite a bit easier than if you were to do this with, say, regular single mode fiber or bulk optics. And so a nice aspect of this experiment is that both the interferometer is controlled by one FPGA device, so it's like the user, and then the wave plates are controlled by a second FPGA device, actually a second computer, and it's like the Oracle. So it's really kind of taking adhering to the structure of this computational problem that was developed. And so the goal here is you have this table of possible unitaries. So Y is going to label which set of unitaries are applied in each case, and the goal of the computation is to figure out what the value of Y is, or which column of unitaries was applied in each case. And you can do this in a single use of the quantum switch. And here are some probabilities for different scenarios, and we have 95% success probability, and it's not 99% because you have some errors from the liquid crystal wave plates and so on. This is actually quite a difficult experiment to align because you take the light through free space through these liquid crystals. So yeah, so the point here is that the multi-core fiber technology really allowed this experiment to be done. And I think as far as I know to date, it's the only quantum switch with more than 2 gates. So what I want to talk about now is actually what I think is really nice application of this multi-core fiber, and it's something which we recently put on archive, which is the idea of doing generalized measurements. So as you know, you have the case of projective measurements are just an example of a type of quantum measurement you can do. The more general case are what are known as POVMs. So these are positive operators that sum to identity. And these are, of course, useful in a number of quantum information tasks like state discrimination. You can increase the amount of randomness you generate through these type measurements and so on. So the kind of approach you have to take here experimentally to implement this type of generalized measurement is you have to expand your Hilbert space. So yeah, so you include more, in terms of photons, you include more modes. So, and then you perform, say, a projective measurement in this enlarged mode space. So the idea with the multiports is that you can imagine, say, a multiport beam splitter, so the fiber beam splitter in our case. And so this is described by some matrix U uppercase D. I should have chosen different letters here, but the idea is that your input state is defined among, say, this first lowercase d set of modes, and then you complete the space with these ancilla modes. So the photon is in some state up here, and then you have these ancilla modes which you just send. It's just vacuum coming in here. Then you have this matrix describing the beam splitter, and then you can put a detector at each of the uppercase D output modes and do a projective measurement. And so the result here is that the projective measurement in this larger space is going to give you this generalized measurement in your input space. So for a single multiport device with D modes, there's I mean, you can implement a bunch of different possible measurements, just basically given by the number of ways you can connect the input modes into this device. So it's this binomial coefficient number of possible POVMs. So the POVM elements, which you can then realize, are given by this operator here, and where these states chi are defined as the computational basis states multiplied by this matrix M, which is just the portion of U that acts on the input state modes. So I'll give you kind of an example of this. In our lab, we have this 7-core multi-core fiber beam splitter. So the cores are arranged like this. So you of course can't connect this directly to a 4-core multi-core fiber, but you can connect the input modes using the multiplexing devices. So again, through quantum process tomography, you can measure the unitary device. So this is, I mean, I don't know what kind of matrix this is. I mean, this is what we have obtained. So it's I don't know if there's a name for this, what family of matrices this belongs to. But so with, because we have 7 total cores and we have a 4-dimensional input state, this will give us 35 different POVMs that would be possible. So we chose one of them based on what we wanted to do. And so basically this matrix M looks like this. So it's going to map these 4 input modes into the 7 output modes. So in order to certify this and show that it's a POVM, a generalized measurement, we have this, we're able to do this through a kind of quantum, a communication test rather, kind of game. So the idea here is that Alice is going to prepare one of 7 possible input states. Again, these are 4-dimensional states. She's going to send it to Bob. Bob is going to do one of 2 things. He can either choose one of 7 possible projective measurements. And so these are projective measurements that are 2 outcomes. So they're dichotomic projective measurements. Or he can choose to do the POVM measurement, so which has 7 possible outcomes. So in order to kind of make this into a sort of game or a task, what we do is we give a sort of points for the possible outputs. So in the projective measurement case, we award 2 points to Bob if his input is equal to Alice's input, and he can identify that that's indeed the case if his output is equal to 1. Or analogously, we can assign 1 point if his input is different from Alice's input, and he knows that's the case if his output is equal to 0. So that's just the way that these projective measurements are going to be constructed. In the case that he would implement the POVM, we give him 3 points if the output B prime is equal to Alice's input. And again, the input states are chosen so that could be the case. So when you tally the total number of points that would be available, you get this quantity W here. And so this is constructed this way because this gives you a scenario in which you can use semi-definite programming to maximize over this function W. So basically in the POVM case, the POVM was defined by our beam splitter. Then we can maximize over the possible input states and projective measurements that could be performed in order to see what's the maximum of this function. At the same time, you could imagine, okay, instead of a POVM, what if MX is actually a projective measurement? And you can then maximize over what's the largest value of W possible in the projective measurement case. And the point here is there's going to be a gap between these 2. So through measurement through this kind of game, we can show that this POVM is indeed a generalized measurement and not a projective measurement.
Steve, can I ask you something?
Please.
That's really very interesting. So I mean, the idea is that you want to certify that you have like a target POVM, right? And then yes. What you're saying is that you can build some sort of communication task and a sort of kind of like bell violation, not a bell violation, but some objective function to maximize that is maximized only by that one POVM, right? That's the idea.
Yeah.
And you can do that with a gap, kind of like but sorry, but then I mean, if you have a POVM that is very close to that one, I mean the value of the objective function, it will be continuous, right?
Yeah.
Okay, so when you said a gap, sorry, I didn't get that part of the gap. Sorry.
Okay. So the gap is, so if you maximize this function over the restriction that the measurement M is a projective measurement, you can achieve a certain number.
I see. Okay.
Then so if M is no longer projective, you can go beyond that.
I see.
So yeah.
Cool. Very nice. Very interesting.
So the reason we chose this particular POVM, I mean, we had 35, just by changing the fibers around, we had 35 different options. We chose this one because it's the one that was most distant from this projective measurement limit.
Okay. Yeah. Cool. Nice. Thank you. Very nice. Sure. Thanks.
So yeah, so this is the idea, and actually is Armin Takavoli who developed all this idea of the task and did all the optimization and so on. So yeah, so the experiment is like this. So again, it's this 4-path interferometer, but now we can Bob can either use a multicore fiber and phase and intensity modulators to produce a projective measurement, or he can connect the 7-core fiber beam splitter and do the POVM. So we have one system or the other to test. And again, we have really high quality interference in these cases. So here's just an example of data. So you can see that. So here's one particular instance of one of the projective measurements. Here's all 4 possible output results. Of course, we group the 3 lower one, the 3 smaller bars together. That would be B equal to 0, and then the B equal 1 case is this taller event. And so then here's, of course, the POVM. So the experimental values we obtain are really close to theory, thanks to the quality of this interference. And so here on the right shows what I was talking about. So when you maximize this W function over projective measurements, you have this bound of 62.5 something. There's actually a bound for non-projective measurements is the top here. What we expect from our experiment is here, this line here, 62.6982, something like that. And what we obtain in the experiment is given by the point here, some error bar. So with by more than a couple of standard deviations, we're above the projective measurement bound. And so I mean, we can certify that we have this generalized measurement. So yeah, this is actually, I mean, I think this is this is say like the first direct, to my knowledge at least, the first direct implementation of a POVM for a system of dimension larger than 2. So yeah, and this is, of course, thanks to this multi-port beam splitter, which in our case is in these multicore fibers. So how much time do I have now?
Steve, let's say 10 more minutes altogether.
Okay. Yeah.
But sorry, one more question. So I mean, here you're saying, so this type of certification is like kind of like there is some degree of device independency here, right?
Yeah, yeah.
Because I mean, if you trust your measure, if you trust your tomographic devices, you could simply take any POVM and tomographically reconstruct the POVM, and that's fine, right? But the whole thing here is that you do it device only from the statistics, right?
Yes.
From the classical outcomes of the measurement. Okay. Cool.
Yes.
I see. Thanks. Yeah.
Exactly. Yeah.
So yeah, more or less like, I don't know, 5, 6, 7 more minutes, so we can leave a couple more minutes then for questions. If you can wrap it up in 6 or 7 minutes.
Yeah, that's perfect. So I'm going to skip something. So I just want to mention, so we've been working on 2 photonic experiments. I just want to skip something here and go to this. So again, in the spirit of telling you what we're doing and incentivizing you to collaborate with us, we have last year we built a source of photon pairs of say higher dimensional photon pairs using this multicore fiber technology. So basically the idea here is we have a nonlinear crystal, and we take our pump laser beam, which you typically use in spontaneous parametric down conversion. We send it through one of these multicore fiber beam splitters, and so that it illuminates all 4 of the cores of the beam splitter. Then we produce an image of the cores onto a nonlinear crystal, so that basically the crystal sees 4 of these spots. And because the photon pairs are born together at the same place, this means we produce correlated photons. So both photons are produced in the same core. So this would be a 4x4 dimensional entangled state. So we then couple the down converted photons back into the multicore fiber and send them away. So then with different measurement devices, we can do measurements in different mutually unbiased bases. And here's some data. So we have fairly high say contrast in these mutually unbiased bases measurements. And this is again performed using these multicore fiber beam splitters. And yeah, so this is kind of just a technical comment about this is what we're doing. But so right now in the lab, we have some new equipment, and we're trying to expand this source for more than a single photon pair. So we're building a 4 photon source, and then hopefully eventually a 6 photon source, and so on. So we're looking to do multi-photon experiments with this in this multicore fiber structure.
So how many photons are there here in this application, Steve?
So there's only two. So this is something we
Uh-huh.
did. We actually did this experiment, say the eve of being in lockdown for a few months. So this was done actually before the university closed for the pandemic. So here there's only two photons right now. So we currently have a pulse laser and so on. We're trying to do the same thing, but with 4 photons.
I see. Cool.
And so yeah, so we're playing around with different setups to say, okay, is it, do we produce these photons separately with 2 parallel sources? Do we try to produce them all together in the same core? There's a bunch of technical details here, which makes it's actually a lot more non-trivial than I imagined originally. I thought this would be really straightforward, and it's not. You have problems when you want to couple, a pulse laser, high intensity pulses into these cores. It's not so easy. We've essentially melted some fibers already. So yeah, so that's something we're working on. And so coupled with that, I want to just kind of finish here telling you about like what's currently going on in our lab and what we want to do. We were closed down the university was closed for roughly a year or so. And so, all of our projects have been delayed a little bit, but so over the past few months, we have made some progress in terms of infrastructure, which we had been building. So one thing which is exciting is that we're just finishing the installation of a multi-core fiber link in our university. So it's I have here down it's 800 meters of fiber, but I think it's going to be closer to a kilometer by the time we finish. So, and the interesting thing here is it's built in a way that we actually link 4 different laboratories together with this multi-core fiber. So there's actually 3 laboratories in the physics building. So there's 2 laboratories on the 2nd floor, which are linked by about 20 meters of fiber. And then we have about 100 meters of fiber going up to the 6th floor, which is nice because the 6th floor actually has access to the roof where we could send information, through free space also to somewhere else in the city, which is something, maybe we'll do down the line. But then another section of this multi-core fiber cable comes down below the ground and across the campus to the electrical engineering building where we have an optics lab. So, and it's about 700-800 meters between these 2 buildings. Goes right under the fountain, actually right next to the fountain. So yeah, so we'll have these, say, 4 links, and the idea here is we want to have some sort of do experiments with say quantum networks and so on, where we can do multipartite experiments with this link. And so this 800 meters, if you're talking about optical fiber, doesn't sound like very much, but in terms of multi-core fiber, in an academic setting, I think this is one of the longer links. I know there was a 600-meter link in Italy, and I heard recently that I can't recall now which telecom company had a few kilometers of multi-core fiber installed. So this is, there's a few places in the world that have this sort of thing going on, and so we're excited that we have this. And so we actually want to be able to rent out this link to local telecom companies and so on. Yeah, so that's something that's going on. And so in the same context, we have some new, say, non-trivial equipment. So we, as I mentioned, we have this pulse laser and also these high efficiency superconducting detectors that for doing multi-photon experiments. So this is all, the pulse laser we've been using for about almost 6 months or so. The detectors are in the process of being installed because they need a lot of water for cooling. So that's been kind of a little bit of a task here at the university to get that installed. And then another nice thing we have is we have this really nice programmable fiber splicer. So instead of having to talk to a company to make these multi-core fiber beam splitters, we'll be able to make them ourselves and play around with it and hopefully develop some new interesting devices. So these are, for us here at least, were non-trivial acquisitions, and we're able to do that thanks to the Miro project. So this is kind of where we're heading in the next couple months. So within, I would say 60 days or so, all of this should be operational. The other interesting thing that we have going on here in Concepcion is we have a startup called Secure. And so involved in this are myself and Gustavo, and then also Jose Brito, who is involved in a few quantum startups, and Marcin Pawlowski from Gdansk, the University of Gdansk in Poland. So the main thing which we've done recently is we've built this self-certifying quantum random number generator. So here's a picture of the device, the first version of the device that was built. And this device, we have a collaboration with the local lottery here in Concepcion, which is a fairly large lottery in Chile. So we have had this device at the lottery, and it's been field validated with them and so on. So we're currently in the version of building, this is kind of the prototype. We're in the process of building the second version of the device, which can then be commercialized. So we have some funding through the universities and through the lottery about this. So, so yeah, that's nice. And in terms of, from a research standpoint, the really nice thing here is that there's a lot of different, side technology that we've developed, which I am really anxious to get into our labs, such as controlling these phase modulators in a much better way, and so on. We've built our own detectors and things like that. So yeah, so that's what's, so let me just finish with kind of what I would say are the kind of take-home messages. Okay, but photons are interesting for quantum information, and the fact that this high-dimensional encoding is interesting, but let's say to within reason, kind of defined by your wallet and the size of your optical table. And then, I mean, the main point here is that I really think this multi-core fiber technology is interesting. I think it's going to be the future of telecommunications, whether it's single mode multi-core fibers or few mode multi-core fibers or some sort of other structured fiber, that still remains to be seen. But just because of the simplicity and the fact that you can, just adapt all of the current telecom protocols to the single mode multi-core fibers, I would be really surprised if it wasn't that structure that was chosen. And of course, in pursuit of this, you can from the quantum side, you have the stability, more stability. You can have these high quality beam splitters and so on. It's of course all plug and play, so you can, in terms of fundamental physics experiments, it's all connected, and you're pretty much ready to go with some obvious problems that occur. Yeah, so and kind of the main take-home message I want to give you is that we're always interested in collaboration. We have grants for postdocs and students and so on. And if you want to reach out to me, please do. And then here's my email, and then here's also the website of our Millennium Institute for Optics, which conveniently has this acronym MIRO. So if you are familiar with the painter, or the verb in Spanish or Portuguese is a nice kind of a nice acronym for Institute of Optics. So yeah, so that's it. Thank you very much.
Thank you so much, Steve, for the fantastic presentation. Congratulations also on the amazing work that you've been doing throughout the years, and especially now in Chile since the pandemic. I understand that it's impressive that you've done especially the network of multiple optical fibers through the campus. That's really interesting and promising. I also sorry also that we had some difficulty with the camera. There seemed to be like a battery issue, but now it seems to be solving again. I should also say that since you're mentioning this thing of collaboration, so we had he was connected, James Grieve, the PI of the quantum communications lab, and he had to leave 5 minutes early. He was asking me for seeing the recorded session afterwards, and he told me, "Wow, what a fantastic talk! I'm looking forward to buying some of those fibers and collaborating with you." So I think it was effective in terms of collaboration perspectives. Yeah. This is really fantastic. I don't know if there's somebody in the audience that has some question. I don't know if Rene or Andreas, or I think Rimin has a question there. Yeah, go ahead, Ri.
Hello, I have two questions. One is regarding the fabrication. So you mentioned that they are commercially available, and I would like to know which companies can help us manufacture this kind of fibers, and what's the estimated fabrication time? And my second question is, are there any differences in terms of the chromatic dispersion, polarization, mode dispersion, or attenuation properties compared to the typical single mode fibers?
Yeah, yeah. So in terms of, there's a few, as far as I know, there's a few companies that fabricate these types of fibers. For example, Corning in the United States fabricates this type of fiber. We've bought all of our fibers from FiberCore, which I guess has offices in the United States and in the UK. And yeah, with them, it's been really good. I mean, we, get on a Zoom call with them and tell them what we want. And you can talk directly to some of the technicians, engineers, and so on. And I mean, we had them when we made this fiber for the pump beam. So it had to be different. The beam split had to be different because the wavelength was different. So they really, we told them what they wanted, and they, tried it a bunch of times until they were able to build it. So yeah, it's because it's in this real R&D stage. These multi-core fibers, you can, you have a little bit more flexibility in terms of what you want. So it's kind of, it's really, really interesting. And I have to give all the credit to Gustavo and Guilherme for that. They were the ones who really pushed this. And as far as I know, they were the ones who really pushed to have this first beam splitter device to be built. And so I don't think FiberCore was making beam splitters before they kind of, pressured them to do it. So, but I could be wrong about that, but that's my understanding of the story. Yeah, so the turnaround time has been, fairly quick, say, on the order of a month or so. I mean, it's been really good in our interactions with them. I'm in contact with a group in Buffalo, New York, and they have some collaboration possibly with Corning, I guess, to get these fibers as well. So you can kind of, because it's this R&D stage, you can maybe take on companies as partners and so on, and you can maybe get this fiber also for a fraction of what the cost would be, in this R&D type of collaborative setting. And so the second question about the chromatic dispersion, polarization dispersion. So the nice thing about the fibers we're using is they really are, individual single mode fibers, just like, an SMF28 single mode fiber. There's just a couple of them. So all of the properties, polarization dispersion, chromatic dispersion are all the same as a regular single mode fiber. So I didn't really mention this, but in all the experiments we have, polarization controllers to control the polarization state the entire time. And that's, I think the real, in terms of, some applications, the real revolution will come when we have polarization maintaining fibers, or polarization maintaining multi-core fibers. Then, we wouldn't have to worry so much about the polarization. But yeah, so for right now, we have all this control. And of course, because they are 4 independent channels, if you send light through, you have to, control the polarization of each of the cores. So I mentioned, being able to control the phase, to have light through the multi-core fiber and being able to address each core and imprint a different phase on each core. That's, something that would be really beneficial. I think if you develop that, I think you will be, a very rich person, because the whole telecom industry will want to use this. And I think if you could do the same with polarization control, you could, you would really have something that, you should be running to the patent office if you develop that device.
So what happens nowadays with the polarizations in the different cores? Like they suffer.
Yeah, so the polarization rotates, differently. So we've done we've tried to do some studies to, see how this, there's different ways you can control the polarization, or through, stressing the fiber, bending it in certain ways, or putting pressure. So we've played around with this a little bit, but we haven't, just because of, lack of time and lack of space, we haven't done, real, say, systematic study of how we could control all the polarization of fiber, but in the multi-core fiber. But this is something that we will hopefully do, as soon as, right now we're building our labs on the 6th floor. So, that's one of the first projects we will do, is try to do something in this regard. So for us right now, this isn't so much of a problem, because we have to remove the light from the fiber to modulate the phase. So we control the polarization at this point. But it is something that will be a problem down the line.
Okay, all right. Is there any other question from the audience? Andreas or Andreas? Yeah,
I have
go ahead.
A question concerning the 4-core fiber or the 7-core fiber. You showed the 4-core fiber, for example, was the beam splitter. The 7-core fiber was some really weird matrix How do you produce such a fiber? Do you produce it and measure it, and then you have some matrix, or is it vice versa? So you want to get a certain matrix, and you produce something.
Yeah, so what we've done up to now, because these devices have been produced by these companies. Basically, it's the same process. They take a fiber with a certain number of cores, they heat it and stretch it, and bring the cores together. So the 4-core fiber, because of symmetry, has this nice, really simple matrix, that describes the coupling. Because of the 7-core fiber, of course, the fiber at the center is sort of preferential. It can couple, equally to all of the modes, but, say the core number 1, of course, is going to have a hard time coupling with core number 7, even, as these are brought together. So even though this does have some sort of symmetry, it's not, there's definitely a difference between, the center core and one of these outside cores. So this because of this, you have this different type of coupling. And so this, basically, the device we have was kind of the first thing you do is stretch the fiber and see what happens, right? Something we hope to do with this fiber splicer we have is to play around with this procedure, and really, kind of, go into the kitchen and see what comes out, so try to do different types of tapering and so on to be able to change the coupling of these devices. Yeah, so right now it's kind of, it was done, and this is what came out,
So I don't know if it's possible or not, but in principle, I could think of knotting them together in certain way. I mean, a weird way. There, of course, something else would happen. I don't know if this. For let's say for construction purposes, this is certainly not the proper way, but I want just to ask. So
yeah, to be honest, I don't know. I think you can imagine a bunch of different techniques, you knotting it or trying to double it back or whatever. Yeah, and I mean, hopefully this is the kind of thing we will hopefully do with this fiber splicer we have. So trying to manipulate the fiber in different ways to try to get these cores to couple together differently. Yeah.
So at the moment you don't control the couplings, neither the coupling strength nor the phase, right? There's also, because this is like a beam splitter, so there are phases involved also, right? Like that's why this unitary here that you show has some imaginary part, I guess, right?
Yeah. So when they fabricated the 4x4 fiber, of course, we said, they said, okay, there was a theoretical model done just based on nearest neighbor coupling and so on, and they realized, okay, well, it should be possible to have this canonical transformation, this something like a Hadamard transformation or a Fourier transform, where light couples has the same probability of coupling, from one core into the other 3. So this is sort of was expected, and so when they do this this stretching, they actually have light going through the fiber, so you can send light through one of the modes, one of the cores, and then you have a detector, or 4 detectors rather, seeing the light intensity to all the other 4, and as you stretch it, when you see 25% in each of the cores, you stop. So you're actually measuring this and stretching at the same time. So that's how and that's how we're able to get them. I mean, until you figure out the recipe, that once the parameters of doing this, then you can just do it. But that was the way we got them to make this beam splitter for the different wavelength. They actually did this empirically as they stretch. So
okay,
that's
cool.
Yeah,
great.
And maybe
I think René may have a question. Yes, go
cool,
ahead,
yeah,
please.
a very practical one. So how do you get light into these fibers? I mean, normally you would use, I don't know, a lens and a fiber coupler or so and couple light in. And I also wonder, isn't there an issue kind of with symmetry if you plug the fiber in again? Wouldn't it, because if I have a only one core in the middle and it rotates a little bit. Normally you have this little notch, right, which fixes it. But here, I think if it rotates a bit, it gets heavily misaligned. And so is there new technology involved, or how do you do this?
Yeah, so in terms of the coupling, so the way the coupling we do is just with this multiplexer device. So, if you want to couple light in, I mean, you have your usual, fiber coupler with a lens and all the mechanics involved to go into a single mode fiber, and then that takes you into the multicore fiber. You can, of course, put a multicore fiber in front of the lens and try to couple equally, and this sort of thing has been done. The other question was, in terms of, so these fibers do come with, your typical like FC, PC coupling. So they have the notch, they're compatible with all the usual optomechanical devices. So the orientation is fixed, but of course you always have a little bit of play in the position of the fiber, right? And so this is something, you kind of just manually have to optimize. And of course there are losses. And so any kind of rotation or something like this is quite, a bit more detrimental than in the single mode case. Yeah.
And are people also working on implementing phase shifters like in these fibers? Because it looks like there are many components which are used now for single mode fibers. Of course, it would be brilliant if you could directly somehow, I don't know how, but
yeah, exactly. I think if you have an idea of how to do this, if you can develop this type of device, you should be applying for a patent immediately. I think this would have, you could make quite a bit of money if you were able to modify the phase, inside the multi-core fiber. And yes, of course, this is interesting, just not for quantum applications. This is how you would, encode information in telecom, at least in certain encoding. So yeah, this device does not exist yet, to my knowledge. But I mean, kind of the nice thing of working on something that's also kind of one of the frontiers of telecom is that there's, major companies also working on this type of thing.
I guess that also for these fiber manufacturers, it's been very useful to interact with research groups like you, because they can see what you guys need, and it must have been like a kind of interactive thing to develop this multicore fiber, I guess.
Yeah.
I think this is what you mentioned.
Yeah.
Interesting.
Just another interesting thing, if I can say, like, so typically what we do is when they fabricate, say, these multiplexation devices and the beam splitters and so on, usually we found out a nice way to buy these, just, some of you seem interested in this type of question, is you buy them in a set. So you have, say the input device, the multicore fiber with the beam splitter, multicore fiber, and the output device. You buy them as a set. And so they optimize all of when they do the connectorization, they optimize the transmission. So you have, you have this set, which are connected, among themselves. And then so if you would take, a demux from one set and attach it to a beam split of another set, the coupling will probably be, quite a bit worse. So they do kind of optimize all of the transmission, the alignment when they do the connectorization.
Cool. Excellent. Great. Hey, thank you so much, Steve.